Alright, now that y'all hopefully have a pretty solid foundation on what momentum is and how to calculate momentum and what impulse is and how to calculate impulse and what the relationship between the impulse and the change in momentum is, they can really get on to the meat of why we do momentum. And that is because momentum is really important in collisions. So, suppose we have a box, and this box has a mass of 8 kilograms, and is sitting on a frictionless surface, and it's moving at a velocity of 5 meters per second. And there is another box that is sitting in ahead of this box. Suppose this box has a mass of 20 kilograms, and it is at rest. So what will happen is that this box here, this 8 kilogram box, will travel toward the 20 kilogram box until it hits right there. And there are a multitude of things that can happen depending upon the surfaces between the two boxes. The first thing that can happen is that the two boxes could stick together. And if this right here is a frictionless surface, there's really nothing to slow them down. So if they stick together, then both these two boxes will travel on toward this way with some other velocity. And we'll figure out what that is. If the boxes don't stick together, then one of two things could happen. The 8 kilogram box could now stop. It could be moving at 0 meters per second, and the 20 kilogram box could then continue to move on. This right here is very common in billiards or pool. If you hit a cue ball and the cue ball hits some other ball, and then the cue ball stops and the other ball starts moving. And the third thing that can happen is that after the two collide, the 8 kilogram box could actually repel back in the other direction, and the 20 kilogram box could move the other way. Now, each one of these situations happening is very dependent upon what type of collision it is. But in all these cases, the one thing that we can always go back to is that the momentum has to stay the same because of a certain law. That law being the law of conservation of momentum. And all this says is that when two objects collide, you can really say when two or more objects collide, that the total momentum in the system supposed to be total momentum in the system does not change. So if we have, suppose, I don't know, we have two boxes. For sake of ease of measurements, let's say this is 2 kilograms and this is 2 kilograms. If this is moving at 2 meters per second squared and this is moving at rest, then the total momentum for the system will be the momentum of this box here, box 1, and the momentum of box 2. So this will be mass 1 times velocity 1, and this will be mass 2 times velocity 2. So if you were to add these two up, these two boxes, being that these two boxes are the only boxes in the system, the total momentum of the system would be 2 kilograms times 2 meters per second plus 2 kilograms times 0 meters per second, which again is 4 plus 0, which is equal to 4. So that says that if these two boxes are in this situation, before they collide, then the total momentum of the system is going to be this 4 kilogram meters per second. And since this momentum right here is 4 kilogram meters per second, whatever combination of velocities that this box and this box have after the collision, the momentum of these two objects added up must again equal 4. Now, suppose that the two boxes are moving some other direction. Let's suppose we can have these two boxes. One is moving at 2 kilograms. You can't move with a kilogram. One is moving at 2 meters per second. 2 meters per second to the right, and the other one is moving at 1 meters per second to the left. Now, we're going to say this is our system, and that it's going to be closed, and I want to figure out what the total momentum of this system here is. So, again, we have box 1, box 2, so the momentum for box 1 be equal to mv. The momentum for box 2 will also be equal to mv, where this mass is 2 kilograms, and this velocity is 2 meters per second. Now, notice that these two are going in opposite directions. Now you know velocity is a vector, which means we need to set a positive. So, let's say that the positive is to the right. So, that means this right here will be a positive 2 meters per second, and this right here will be a negative 1 meters per second because it is moving to the left. So, when I added it up, my handwriting is terrible here, I apologize for that. When I added this momentum up, again my mass would be 2 kilograms, but my velocity now is going to be negative 1 meters per second. So 2 times 2 over here is 4 kilogram meters per second. And 2 times negative 1 will be minus 2, or negative 2 kilogram meters per second. So when you add 4 and negative 2 up, what you'll get is a positive 2 kilogram meters per second. So that says that after these two boxes collide, that the total momentum of the system has to be this positive 2 kilogram meters per second. There can be any variation of masses and velocity between these two objects, but when you add them up, it has to be this positive 2 because that's what it was to begin with. So, going back to our law of conservation of momentum, it just says that when two or more objects collide, that the momentum of the system doesn't change. And there's a formula that we like or that I like to discuss when we talk about this. I'll try to slow down because I know I speak fast sometimes. That's all the law of conservation of momentum says is that m1v1 plus m2v2 equals m1v1f plus m2v2f. So, this right here is the law of conservation of momentum that is used with basically a two-object system. Now, the vast majority of the things we deal with in this class are going to be two-object systems when we're talking about collisions. I don't really want to give you all objects that, are collisions that have 3 or 4 or 5 objects. Even though that does happen quite often, especially when we're talking about gas particles moving around. They collide with each other at a very high rate. But for this purposes in this class right now, we're going to talk about two objects. So, each object is calculated twice. The first object is calculated at the beginning and at the end, and the second object is calculated at the beginning and at the end. This side of the equation here is the adding up of the momentums that we did in these past couple slides. Basically here and there. It's that same M1, V1, M2, V2. But these right here are all initial settings. The M1, V1F and M2, V2F are basically the momentums of these same objects, but on the final setting. So this right here would be before the collision. If these two objects were to collide, before collision, and these right here would be after collision. So, let's do a simple problem right quick. Let's suppose that we have our two boxes. And this is the before time. Again, each box is 2 kilograms. This box is moving at 2 meters per second, and this box right here is stationary. Now, they collide, this one comes together, there's a collision, and after they collide, this first box, let's call this box 1 and this box 2, this first box, this box 1 right here, is moving backwards at 1 meters per second. And this other 2 kilogram box, our box 2, is doing some velocity in some direction. We don't know if it's moving this way or if it's moving that way, but I want to know what the velocity of this object is. So, if we go back to our formula, m1v1 plus m2v2 equals m1v1f plus m2v2f. If I'm looking for the velocity after the collision, I'm looking for this value right there, which means I have to know what this value, this value, this value, this value, this value, this value, and this value here is. And I do happen to know all of those values. So, let's do a little solving real quick. So, I'm going to start, new slide, by writing up my equation up here at the top. Alright, so, again, left side, this is before the collision, this is after the collision. We've talked about that quite a bit so far. So let's go ahead and plug our values in. So to check these values, let's go back to our picture. Each one of the boxes has a mass of 2 kilograms. So let's go ahead and plug in those values for all of our masses all the way down. So this mass here, 2 kilograms, 2 kilograms, 2 kilograms, 2 kilograms. This is kind of easier when both your boxes are the same. I'm not going to go ahead and put this in parentheses. And now let's go back and look at our velocities. So before, our first box, this box here is moving at 2 meters per second. So I'm going to put in 2 meters per second there. And there's my addition sign from above. Now, the second box was not moving at all. So I'm going to put in a 0 meters per second there. And there's my equal sign. So, if I were to simplify this, 2 times 2, which is this side right here, is going to be equal to 4 kilogram meters per second. And 2 times 0 here is going to be 0. And you don't have to worry about units because there's nothing. So, our second side says we have 2 kilograms, but we want to know what this first velocity is. So if you go back here and look at it, this right here is 1 meter per second, but notice it's to the left. Now, up until this point, I've said that this 2 right here is positive, which is making the assumption that positive is to the right. So if positive is to the right, and this right here is going to the left, that means this right here has to be a -1 meters per second when you're talking about equations, because it's going against the positive direction. You should know against the positive is negative. So I can plug in a -1 meters per second there. Kind of jam myself in here. Let me expand this right here just a little bit for y'all. And I'm still looking for this final velocity there. So, a while ago I moved my 2 times 2 on there, my 2 times 0 there. Let's go ahead and move this down. 2 times -1 is going to be a -2 kilogram meters per second, plus this 2 times VF. And I'm really looking for this VF value right there. So I'm going to just go ahead and write down 2 VF. And you can really leave this right here as kilograms if you want to. So, this tells me that 4 plus 0 equals 2 kilograms per second, or excuse me, -2 kilograms per second times 2 times some velocity. So, first thing we need to do is we can get rid of this right here because it's 0, and poof, it goes away. So 4 kilometers per second equals -2 plus 2 VF. So the first thing I want to do is add this 2 kilogram meters per second to each side. That's supposed to be a kilogram meter per second there. It's terribly, terribly written. So add it to each side. This gives me that 2 plus 2 is going to be 6 kg meters per second is equal to 2 kilograms times VF. And I want to know what that VF is. So to solve for that, I divide each side by 2. And 6 divided by 2 gives me a final velocity of 3 meters per second. So if you notice, that is actually going to be a little bit faster than this first box took off. And that is fine, because since this other box is moving off in a different direction, the momentum is still conserved. So, now if you remember earlier when I was talking about the two boxes back here, I told you that there were 3 different things that could happen. 1, they could stick together. 2, one could stop moving and the other ones could continue moving on. Or 3, they could move off in opposite direction. Now these right here really correspond to the 3 different types of collisions that we'll have to learn in this class. The first one being what's called an elastic collision. Now, when you have an elastic collision, really 2 things are being conserved here. Momentum is being conserved because it's a collision, and every collision momentum has to be conserved. And since it's elastic, we can say that the kinetic energy is also conserved. So if you want to define this right here will be a collision where momentum is conserved. And where kinetic energy is conserved. Now, I forgot to write energy in there. Kinetic energy is conserved. Now, this right here is probably the least common type of a collision that you can really see in real life. But there are a couple of places where this very commonly occurs. One of the places is in billiards, or pool balls. Pool balls roll on a felt surface, and they are very hard and have a similar mass, almost identical mass to each one. And the surface and the mass and the texture of the billiard balls allows the kinetic energy to be conserved most times when they collide. And this gives pool balls some really interesting characteristics. Ones that you can accurately hit a cue ball into another ball because the surface. And most collisions, if they're not straight in one line, which is what we're dealing with now, if they go off into angles, as a general rule, that angle is a 90-degree angle, which again has to do with the kinetic energy being conserved, which lets them be very predictable and lets you be able to actually aim your shots. The other place where elastic collisions commonly occur is in gas molecules. Why is my handwriting so bad tonight? Alright, gas molecules. These right here are really small particles. They're flying around in air, and they hit each other really fast, and they bounce off, and there's really no energy lost, which is a good law of thermodynamics, which we'll get in later this semester. But I want to expound upon these pool balls right here. So, let's suppose that you have a billiard table, and I don't know, you're playing somebody in billiards, and you have the last shot. It's a shot to win the game. So you have an 8 ball. It's a black 8 ball. It's got 8 written on it. And you want to make that 8 ball travel over to a corner pocket. Or a side pocket. And is lined up perfectly with the cue ball, which is the white ball. Now let's assume that each one of these balls has a mass of 0.25 kilograms. Which is a pretty close approximation to what cue balls actually are. And you want to hit the cue ball so that it has a velocity of 3 meters per second, which is a quick hit. Now, if any of y'all play pool, you should know that if you put spin on the cue ball, that it can cause some interesting properties to occur. But if you want to just pocket a single 8-ball, you want the cue ball to stop as soon as it hits. So the cue ball flies to the object, it hits here, and then the 8-ball object continues on. So after the collision, this will be before. So after the collision, what you have is the cue ball sitting right where the 8-ball was, not moving, and then the 8-ball is now going to be moving off at some velocity. And I want to know what this velocity right here is. So, to figure out what this velocity is, we use our formula m1v1 plus m2v2 equals m1v1 plus m2v2. Now, let's say that the cue ball will be our first object and the 8-ball will be our second object. So the first thing we can do here is we can look and say, hey, there are no velocities at 2 spots. So initially, this is after down here, initially our 8-ball is not moving. So on our initial side, object 2 has 0 velocity, which means I can cancel it out. And after the collision, the cue ball has 0 velocity, so this velocity here is 0, which means I can cancel this out, which greatly simplifies my formula. m1v1 equals m2v2. Basic, simple enough, right? So if I plug in my value of my cue ball, 0.25 kilograms, and the velocity that it had to begin with, 3 meters per second, and I plug in the value of my 8-ball, which is again was 0.25 kilograms, and I'm looking for my final velocity. Again, there's the values of each one. And this right here should be a very easy problem for you to do. You should notice that if you divide each side by 0.25, that the two velocities should be the same. Simple enough. This right here is a basic tenet of pool. Now, this right here just followed this simple conservation of momentum problem. So what made it elastic? What makes it elastic is that the kinetic energy before has to equal the kinetic energy after. So if we take this picture right here and we calculate the kinetic energy for each side, we'll get, well, let me just show you what it's going to be. Let's do a little table. Kinetic energy, we have 2 objects, object 1, object 2, we have before, and we have after. So, kinetic energy is equal to 1/2 mv squared. So object 1 before, our kinetic energy will be 1/2 times 3 meters per second, excuse me, that's mass. 1/2 times 0.25 kilograms times 3 meters per second squared. This right here is going to be 1/8 of a ninth, which is let me calculate right quick. And my calculator doesn't work. Screw it. Let's say this right here is going to be 9/8. Simple enough. I should be able to do this in my head. This is 1.125. And this right here is going to be joules. Now, object 2 initially is not moving, so it's 1/2 mass times 0 squared, which is again 0. So if I were to add these two up, I would have 1.125 plus 0, which is a total. It's a total of 1.125 joules. Now, afterwards, if we look at our collision, our cue ball stops now. So it now has 0 velocity, so it has 0 joules of kinetic energy. But my object 2, my 8-ball, which has a mass of 0.25, is now moving at 3 meters per second. So if we plug it into the kinetic energy formula, that being 1/2 mv squared, Again, this right here is 1.125 joules. So add up my after energy. 0 plus 1.125 is again 1.125 joules. And since my total kinetic from one before equals my total kinetic energy afterwards, that tells me this right here is going to be an elastic collision. Now, the other type of collision you could have is an inelastic collision. And this right here is what we will more commonly deal with in this class. In an inelastic collision, momentum is conserved, but some kinetic energy is lost. Now, it's not lost forever, but what happens is it gets converted to heat, or it gets converted to sound. It is usually lost. Is lost during the impulse part of the collision. So, let's do a simple problem that is going to be inelastic. Let's say we have a box. And we have a bigger box. The first box has mass of 1 kilogram. The second box has a mass of 2 kilograms. And the first box is traveling at, I don't know, 2 meters per second, and it collides with my second box. And this right here is going to be before the collision. Well, let's say the second box is not moving. Let's make it easy, right? Now, after the collision, the 2 kilogram box is moving off with a velocity of 0.25 meters per second as a velocity. And I want to figure out what my 1 kilogram box is moving at. I don't know what it is, so let's figure it out right quick. So, we need to use our law of conservation of momentum to figure this out. That is going to be m1v1 plus m2v2 equals m1v1 plus m2v2, where the left side of the equation is our before, the right side of the equation is our after. So, look at our picture. Initially, object 1, let's call that the 1 kilogram box. Let's call object 2 the 2 kilogram box. The object 1 box has a mass 1 kilogram, has a velocity of 2 meters per second squared. Excuse me, 2 meters per second, not squared. And our second box, this one here, is moving at 0 meters per second. It's not moving at all, which means it has no momentum, and that cancels out. So, after the collision, our first box, our mass 1, again is 1 kilogram. And I'm looking for its velocity. I don't know what it is, so I'm going to put a v there. And then we'll add to the second box, which is a 2 kilogram box, which is moving at 0.25 meters per second. So, first thing I want to do, figure out what this velocity here is. 1 times 2 is 2, which equals 1 kilogram times v, plus 2 times 0.25. Well, a quarter of 2 is going to be 0.5 kilogram meters per second. So, what I need to do is subtract this 0.5 from each side. And I get that 2 minus 0.5, that's really bad handwriting. I need to get a better stylus for this thing. 2 minus 0.5 is 1.5 kilogram meters per second, which is equal to 1 kilogram times v. So to solve for that, I want to divide each side by 1, and my velocity equals 1.5 meters per second. So if we look at our kinetic energies this time, so again I'm going to do a before and after object 1, object 2. And we're going to do a kinetic energy graph. So let's look at what's going to happen with each of these kinetic energies before and after. So, initially, object 1, 1 kilogram, 2 meters per second. So to calculate kinetic energy, which is 1/2 mv squared, you can say 1/2 times 1 kilogram times 2 meters per second squared. 2 squared is 4, half of 4 is 2 joules. Object 2 is not moving. 0 joules. Alright, let's look at our after. Afterwards, object 1 is now moving at 1.5 meters per second. So we have 1/2 times 1 kilogram times 1.5 meters per second squared. That I actually have to put in the calculator. Which is going to be 2.25 joules. And my second side is going to be this right here, which just says that it's going to be 1/2 times 2.25, excuse me, 2 kilograms times 0.25 meters per second squared. Again, if I multiply these together, this tells me this is going to be 0.0625 joules. So if we look at our befores are equal to 2 joules total. And our afters are equal to 2.3125 joules. Now notice that this value and that value are not the same. That tells us that's not an elastic collision, or it is an inelastic collision. So when you're looking at how to figure out whether you should do something with the elastic collision or inelastic collision, notice that both these collisions use the formula M1V1 plus M2V2 equals M1V1F plus M2V2F. Always start with this, because this formula here will never lead you wrong. Now, last type of equation. This is my favorite because it's, I don't know, it's easy to work. And that is if the two objects stick together. We call this a perfectly inelastic collision. Wow, that's terrible handwriting. Two objects stick together. There's no E linked together. Now, this says that if you have, let's suppose, using the same problem as last time, we have a 1 kilogram object that's traveling with a velocity of 2 meters per second, and it collides with a 2 kilogram object which is at rest. And then after they collide,